Okay, so we have this decomposition of the field, and now what we want to do is we first of all want to substitute this in the action. So we have S Euclidean of lambda. Now I substitute this in. And when I work this out, I will get three pieces. So one piece will be S naught of phi lambda prime. Then I will have plus S naught H plus S int phi lambda prime plus H. Okay, so why do I get this structure? Yeah, so this obviously is the same as S naught of phi lambda prime plus H.
Because you can split in that part.
But how can I split? Because it's quadratic, but I also will get pieces like phi lambda prime times H. Dx phi lambda prime times dx H.
It's a free theory, so the momentum modes decouple.
It's free theory, and by momentum conservation, the cross terms have to cancel.
Exactly. If you transform, then you see.
Exactly. Yeah. Exactly. Okay, so this is the form we have. Good. Now what we do is we substitute this into a path integral. So then we have now z lambda, okay, becomes, okay, so that's this. So z lambda becomes d phi lambda prime dh, because it's just a decomposition in the space of the modes. This will be the same as the integral over all the modes by construction. And then here I will have e to the minus S naught of phi lambda prime minus S naught of H minus S int. Yeah, and then what we'll do is we'll reorder this a little bit. So this becomes d phi lambda prime. So I take this out, e to the minus S naught phi lambda prime. And then here I get now the path integral only over the sparse degrees of freedom H. E to the minus S naught of H minus S int. So far nothing much has happened. But now this quantity here, is like an average, because that's what the path integral is. It's an average over the vast degrees of freedom of this quantity here. Sorry, of this quantity here. So in other words, this I can write as ZH times the average of e to the minus S int with regards to these vast degrees of freedom. Yeah? So this ZH just would be the fast part of the partition function, so this would be d h e to the minus S naught H. Yeah. Okay, and the average of some operator, whatever it is, with regards to these degrees of freedom, by definition, is 1 over ZH integral dh e to the minus s naught of h. Oh, okay. So what we have to do, in other words, we have to average this interaction piece here with regards to these fast degrees of freedom. Okay. Now, what I said we wanted to do was to essentially work out how integrating out these fast degrees of freedom would affect the slow degrees of freedom. Yeah? So I want to know, if I do this path integral here, how does it change the action for the fast degrees, for the slow degrees of freedom? Yeah? And so integrating out h, also the fast degrees of freedom, gives what's called an effective action for these phi lambda prime degrees of freedom. And this effective action of the slow degrees of freedom by definition is just the free part, so S naught phi lambda prime, which is what's written here. Yeah, plus whatever I get from here. Yeah. But so here I get this average, okay, and in order to look at how it changes the action, I have to exponentiate it. Yeah? So what I get here, in effect, is minus log of the average over the fast modes, e to the minus s in phi lambda prime plus h. Okay. So this is very general. Okay. And in principle, so you can write this formally for any theory you like. Now, the trouble is, okay, so you have to work out this object here. Okay? Now, in practice, in order to work out this object, what you have to do is you have to use perturbation theory. So this interaction part of the action had a parameter, this lambda parameter. Yeah? So now let's assume this lambda is small, yeah? And just expand this quantity here. So now we must resort to perturbation theory. In our small parameter lambda. Okay, so what I do is I will expand this, so e to the minus s in phi lambda prime plus h, average over h is 1 minus s in average. And then the next piece would be essentially, now I have 2, I get okay, so plus a half s squared in phi lambda prime plus h h plus dot dot dot. Okay, but what I need is actually not this expectation value, but the log. And now I simply use the expansion of the log. You have log 1 minus, and using that lambda is small, basically this average should be small. It's proportional to lambda. So I formally now will expand the log. So log e to the minus s int becomes minus s int and now I get two terms plus a half s squared int minus s int squared plus dot 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 dot. Okay. So far so good. Now what we want to do is we want to work out, for example, this quantity here. Yeah. So if you do this actual calculation, you can do this to higher orders, that's absolutely fine. It corresponds essentially to a loop expansion. Yeah? So the subsequent terms, there will be higher and higher loops. You can formulate it in such a language. Which also tells you that the higher order calculations become more and more complicated. So usually one goes basically to this order and then one stops. Let's even look at just at the leading order, because most of the information is already there. So now let's calculate this average. So what is it? So it's lambda let me just write what I have here, d squared x. So I think I changed notations to what I wrote for you last lecture. So I dropped this one over a naught squared and I absorb it in the definition of the small parameter lambda. So sorry about that. So here I have a cosine beta phi lambda prime of x plus beta h of x. And I want to average this over h. Okay, so what is this? So this is equal to lambda divided by 2 d squared x. So now I just write this as e to the I beta phi lambda prime of x, and here I need the average of e to the I beta h of x plus function conjugate. So I just had expanded the cosine. Okay, so now we have to work out what is this object here. Okay, so what is this object? So e to the I h of x averaged over h, by definition is just 1 plus I h of x average over h minus a half h squared of x average over h plus dot dot dot. Okay? Now this one is equal to 0. Why is it equal to 0?
Because the distribution is Gauss.
Yeah, because we take the average with respect to a Gaussian theory, which is invariant under h goes to minus h. So this is 0. Okay, so what about this one here? How do you work this one out? Well, the easiest way is you just go to momentum space. Yeah, so then this becomes 1. I drop the beta squared. Minus beta squared over 2. And here then I get the integral in my slice. d squared k over 2 pi squared h of k h of minus k. Plus dot dot dot. So all I do now is I go to Fourier space. Yeah? So h of x equals integral dk blah blah blah. Yeah? And that gives me the Fourier transform here. Okay? But then you have to use that the only non-zero Fourier modes for h, because it's the fast degree, which will occur in this slice. Okay? All I do is now a Fourier transform, I haven't done anything else. Still a quadratic theory. Okay, but now we use the average is with respect to a Gaussian theory. Yeah? And we know what is the propagator in the Gaussian theory. So the two-point function of the Gaussian theory, so it's just 1 over k squared. Okay? And now, this is a simple integral to do. You just go to polar coordinate.
Why do you make an expansion in h, in power of h?
I don't have to, but you'll see in a moment. Yeah,
because
I know I don't have to. So I wanted to do it for a reason, because what will come out is that what I have here is actually small. Yeah, and the only terms I want to retain in what I'm doing is actually this term. The higher order terms I actually want to throw out because they're small. That's why I expanded. It's a Gaussian theory, I know I don't have to do it, but it gives you exactly the piece that you need.
Okay.
Yeah? So just let me write the next line and maybe, if it's not clear, just ask again. Yeah, so this is 1 minus beta squared over 2, and here I get dl, and these extra terms here, the higher order terms, they would be of order dl squared. So they're much less than this, and this dl, I have to find here, is in fact ln lambda divided by lambda prime, and this is ln 1 minus lambda prime divided by lambda prime, right, plus, that is correct, and so this is approximately equal to lambda minus lambda prime divided by lambda. And now you see this is infinitesimal, so to speak.
Yeah,
right?
so if you just want the beta function in the end,
Sorry?
if you just want the beta function in the end, you just
Exactly, that's what I do. I'm not going to do more at this stage.
Because you don't have to make an infinitesimal rescaling.
Okay, so as I said, so you can do this calculation in many different ways. So this is a very kind of pedestrian way of doing the calculation, which gives you exactly, as you say, the beta function, which is what I want to calculate. All right, so I've done this. So now we can put everything together, okay, because this was the most important correction to my effective action. Okay, and writing it out explicitly, I get S effective of phi of lambda prime is as naught phi of lambda prime plus lambda, and here I have 1 minus beta squared over 4 pi dl, and here I get the d squared x cosine beta phi lambda prime. Okay, so basically what you see is by integrating out these hydrogen degrees of freedom, you renormalize the coupling constant. Okay, so there's a coupling constant renormalization. And now if you go to the next order, to the one loop order, you also get a wave function renormalization. You get a z factor for the field. But I'm not going to do that calculation, it's straightforward. You can also look this up. For example, in the book by Gogolin, Zwerlik, and Assessian, which I'm really following here. Okay, so we have this, and now to complete the RG scale, to complete our RG step, we must rescale momenta and positions to recover our original cutoff. So what we have to do is we have to rescale momenta according to k goes to lambda divided by lambda prime k, and x goes to lambda prime divided by lambda x. So it's the inverse rescaling. And this is, as you always do in RG, because what you do is you coarse grain, which is what we have done here. So this corresponds essentially to coarse graining in position space. After you have done it, you want to recover your original scale, so you rescale coordinates. So if you do this, the effective action of phi of lambda then becomes the Gaussian part plus lambda 1 plus 2 dl, which comes from the rescaling, minus beta squared dl over 4 pi dx cosine beta phi lambda. Okay? Now importantly, so that's essentially the same theory as we started with, but we have to change the coupling constant, we have to renormalize it, so the new one is the old one plus the old one times 2 minus beta squared over 4 pi times dl. Okay? And now we can write the renormalization group equations for the coupling constant. Okay, so let's define an L-dependent coupling, lambda of L. Then I can rewrite this equation as a differential equation. So d lambda by dl is actually lambda of L times 2 minus beta squared over 4 pi. And the initial condition is simply that lambda of 0 was the bare coupling constant lambda. I started with that in my head. Okay, so this might not look like much, but it actually tells you an awful lot about the effect of this term. And that's really what I'm after. Okay, so you can just solve this equation. So this tells you that lambda of L is lambda of naught times e to the 2 minus beta squared over 4 pi L. Now you see this coupling constant, so lambda of L, it's the running coupling constant now, lambda of L, it behaves very, very differently depending on whether this exponent here is positive or negative. Yeah? And that basically now divides the physics of the model into two regimes. So the regime 1 would be beta squared is larger than 8 pi. Okay, so then you see the coupling constant actually gets smaller under renormalization. So this tells you that lambda of L gets smaller as L is increased. An increase in L means going to lower energies, larger distances. Okay, so in this case, the importance of this cosine term becomes less and less and less and less as I go to larger distances. And so, for example, when we calculate these correlation functions, we were interested in how they behave at large distances. Okay? And now if your perturbation is such that beta squared is larger than 8 pi, in that regime, you simply can forget about this cosine term because its coupling constant, this lambda of L, just goes to 0. Yeah? So such perturbations are called irrelevant. And that's exactly actually what happens in this XXZ chain with this cosine term. So, close to the XX point, we had this extra piece, which was the x cosine square root of 16 pi phi minus 4kf x plus a naught over 2. We had something like this. Yeah? For the XXZ chain in small delta. Okay? And now, you see, irrespective of actually what happens with kf, the coefficient here in the cosine term is square root of 16 pi, which is larger than square root of 8 pi. Okay? So therefore, this perturbation is always irrelevant in the RG sense and will not be important, will not affect the large distance asymptotics of the correlation function. Yeah? So therefore, I can drop this. And irrespective of actually whether this oscillates or not. Now the other regime was beta squared less than 8 pi. Then lambda of L grows under RG. So these perturbations are called relevant. And that means the cosine term actually changes the physics at large distances. Because at large distances, this cosine term will be very, very strong. Yeah? And so in particular, so it will dominate the physics, right? So you will have a cosine beta phi, and if it's relevant, a good approximation to see what happens to the model, just go to the classical limit, yeah, where you minimize this potential. Yeah? That's the first step. Now, let's assume our perturbation is relevant. Okay, so this leads to the generation of a finite correlation length so the model ceases to be critical, because the Gaussian model, of course, is critical. Okay, so now for the quantum theory, finite correlation length means there has to be a spectral gap. Okay, and now one very useful consideration, it's very, very simple, but nevertheless very useful, is you can estimate how your spectral gap actually scales with lambda, the scale coupling constant. Okay, so for the quantum theory, i.e. real time, so we get a spectral gap, which I call M. Okay, now let's estimate. M. Okay, first you have to recall that dl was essentially d log lambda. Yeah? So L itself is actually not the scale, e to the L is the scale, so to speak. Okay, so then identify e to the L naught okay, so then identify e to the L naught. Okay, let me just write something else. So going back to our solution of the differential equation, we had lambda of L was equal to lambda of naught times e to the minus 2 minus beta squared over 4 pi L. Okay? So now, at some value of lambda, of L, this coupling constant lambda of L will actually become 1. Okay? So let's say we start with a Bayer coupling constant which is very small, which is quite often the case. But then under renormalization, the coupling constant actually grows. Okay, this is better. Yeah, the coupling constant actually grows until eventually, at some value L naught, lambda of L naught becomes 1. Okay? So at that point, our whole approach, which was based on expanding for small values of lambda, ceases to operate. Yeah? You can no longer trust it. It's not, you have left essentially the perturbative regime. Yeah? So the whole approach breaks down. Okay? Now this happens at some particular value of L naught. Okay? And now, in order to estimate the correlation length, it's very reasonable to assume, as an order of magnitude estimate, that value of L naught, yeah, or more precisely, the cutoff, which is related to e to the L naught, is equal to the finite correlation length that is generated by the relevant perturbation. So let me write this down. So e to the L naught at which lambda of L becomes of order unity, and our perturbative approach breaks down with correlation length. So measured in units of 1 over the cutoff. So in other words, we say L naught is log lambda times psi, where psi is now our finite correlation length. So the basic idea is, okay, so what the relevant perturbation does is it generates a length scale. That length scale is psi. Alright? So now when does this happen? Well, a good guess, the best guess we can do on the basis of this analysis is this correlation length gets generated when the perturbative approach actually breaks down. Because then you're certainly no longer scaling variable. Okay, so that gives you this condition, and now you combine essentially this equation with this equation, and this gives you an estimate for the correlation length in terms of your short distance cutoff. So
but when you look at just the RG equations, it could very well be another triple phase on the other side, no?
No.
No?
No.
What tells you that?
So essentially, well, not for this model.
Yeah, but looking at this.
So in general, what can happen is, okay, some of the degrees of freedom, okay, get gapped out. This is what the relevance of the perturbation actually means. Okay? So certain of your low energy degrees of freedom become massive. That is necessary. Now what you are saying is, how do I know that all of my low energy degrees of freedom become massive? And indeed, this is generally not the case. Yeah? So you could flow from some critical theory to another critical theory which has a smaller central charge. So this is allowed. Yeah? Okay? For this particular case, actually this doesn't happen. So how do I know it? Well, because essentially you just have this one operator, yeah, which is relevant. The analysis you can always do is you basically say, okay, now if lambda becomes huge, okay, so I have the kinetic part, and I have the potential part. Yeah. So now just imagine that lambda is not 1, but lambda is 1,000,000. Yeah. So then essentially you can do a classical analysis. You just look at the minima of the potential, and then see what a little bit of kinetic energy does. But this one basically makes the theory non-critical. Yeah? So this is a hand-waving argument, but for this particular case, this is how it works. And the case you have in mind can also be analyzed by variants of this this theory, the scaling theory. So that is known. You can look it up on Wikipedia. I suppose it's called two-cutoff scaling. And essentially, it usually happens if your perturbation is more complicated. Yeah. So you don't just have one cosine, you have several operators which compete. Yeah? And then what happens is one of them goes to strong coupling, yeah? So it's relevant, goes to strong coupling. And then what you do is the degrees of freedom, certain degrees of freedom, they are gapped out by exactly the same mechanism we have here. Then what you have to do is you integrate out now these massive degrees of freedom in the path integral, I mean as we have done before. You get an effective action for the remaining degrees of freedom. And then you repeat the procedure. Yeah? So it goes through, but look, I mean, life is too short. I mean, this one, let me try to get this one across. Yeah, yeah, so I want to finish this estimate because despite the fact that you might think this is a completely crazy estimate, this is actually a superb estimate. Now, 1 was equal to lambda of L naught, and this was lambda of naught times lambda xi, 2 minus beta squared over 4 pi. And so this tells me that the inverse correlation length goes like the cutoff times the bare coupling to 1 divided by 2 minus, if we define d is beta squared over 4 pi, it's called the scaling dimension of the operator, 2 minus d. Okay? And now by dimensional analysis, we can translate this finite correlation length into a gap by just using the velocity. So the gap will be v times lambda of naught 1 over 2 minus d. Okay, so that's an estimate for the spectral gap that the relevant operator induces. Okay, so it's a very kind of rough and ready thing. And you might say, well, I mean, this is useless. So let me show you an example where this gives you actually extremely useful and very precise information of how a relevant perturbation can lead to a spectral gap. But before doing this, let me just come back to my phase diagram. So, phase diagram for the umpteenth time, so it looked like this, minus 1, 1, h, delta. Okay, so now what does this have to do with my Heisenberg model? Essentially, this perturbation, now let's just look at magnetic field equal to 0, in which case I can drop this part. Yeah. Now, once I take interactions into account, I had a phi tilde here, and I had something like 2 divided by r tilde. So that was my perturbation. Okay. Then I gave you a formula from the Bedian-Satz solution. Yeah. How r tilde depended on delta in the last lecture. Now, what happens is this r tilde is precisely such that here the operator, this one there, is always irrelevant. So I can always drop it. Okay? Because essentially this beta here, beta squared would be larger than 8 pi. However, what happens at this point here, the point of the phase transition, beta squared becomes exactly equal to 8 pi. So d becomes 2, which is precisely the border between relevant and irrelevant. Okay? And so what happens here is you have a phase transition. And on the other side, your cosine is actually relevant and opens up a spectral gap. Okay? And the phase here is then this massive, this gap phase. Yeah? And you can understand how the gap scales by this argument. So this basically tells you how the gap scales with delta minus 1. Yeah? Okay, and this would give you exactly the correct answer of how the gap actually grows. Now, here, very close to the phase transition. Yeah, so the issue that remains, I'm not going to do this for you because I don't really have the time, is how do you precisely describe the phase transition? Because what I've told you is, well, from this first order analysis, either the operator is relevant or irrelevant, yeah? And so either I can drop it or I have to keep it. But what happens actually if the scaling dimension is exactly 2, so I'm exactly at this point, I haven't told you. Doesn't follow from the calculation I have done. So what happens in this case, you see that beta squared over 4 pi is exactly equal to 2. So this first order correction to my coupling constant realization just vanishes. It's just 0. Yeah? And then what you have to do is you just have to go to second order in this expansion that I started with. Yeah, where you have this average of s squared minus the average of s squared contribution. That's a one loop calculation, and then you can analyze it in essentially the same way I've done. There's some slight complications, but they don't really matter. And that gives you an improved description of the beta function of the RG equations in the vicinity of this point. Okay? And this calculation then, so this is known as the Costin-Staunus. Phase diagram. And that calculation basically tells you how this transition occurs, right? And as I said, so I don't really have the time to do this. What I want to do instead is what I just advertised. I will show you another example where, based on this very simple considerations here, I can make a prediction, a non-trivial prediction. Yeah, which people doing numerics basically have to work for very hard to verify. So the example, which is also an example in how this visualization approach is useful to study non-integrable models, is the following. So consider a Hamiltonian, which is an XXZ chain. Which we understand now. Let me take this delta between -1 and 1, so in the critical regime. So this we understand. But now let me add a term which makes the model manifestly non-integrable. So I put here a magnetic field, but it's a staggered field. -1 to the n. And let's take, doesn't really matter, let me take Sxn. We study this model. So now you might ask, why would you want to study this model? This looks completely insane. It's actually a model that describes a whole variety of quasi-one-dimensional crystals. What happens quite frequently in such circumstances, well, I probably can also put a uniform field here. If you have a crystal with a low symmetry, usually what happens if you apply a magnetic field in some direction, you can induce a staggered field in a direction perpendicular to the applied field. This happens for quite a variety of materials. So this is a perfectly reasonable actual physical effect. Yeah? And now the question is, okay, so you apply this field, it gives you a Heisenberg chain in the field, which we studied by the visualization approach. Okay, but now let's assume, okay, my crystal is of low symmetry, so I also induce the staggered field. Now the question is, what does the staggered field do? Okay, so what is the effect of H prime? Okay, so now we have all the technology to answer this question in like 30 seconds. All right? Because now, Sx basically was such that it had a staggered component. So we bosonized this. Yeah? It had a piece -1 to the j, and then here I have the cosine 2 pi r tilde theta tilde in these notations, plus other parts. Okay? So these other parts will be rapidly oscillating. There was a 2kF because I have a magnetic field here, so I can drop them, yeah, because rapid oscillations will remain. Okay? So now this is exactly, okay, so now if I go to the field theory, so my Hamiltonian becomes V over 2 integral dx phi squared plus Vx theta squared. Yeah, so that was just the Heisenberg model in the field. And now we have an extra piece, which is h prime integral dx cosine 2 pi r tilde theta. So this model is exactly of the type we just analyzed. So just instead of the field, it was a dual field, but it doesn't matter because as far as this theory is concerned, you can just do a duality transformation and just exchange the field and the dual field. But I mean, the correlation functions don't care about this. Okay, so now you can say, okay, I know now what is the effect of this staggered field. If my compactification radius is such that this is less than square root of 8 pi, I will open up a gap. So I'm no longer critical, I will change the physics of the model. On the other hand, if this is larger than square root of 8 pi, I will remain critical. Okay. So now, the first system this actually was found in, delta was just equal to 1. So it was isotropic Heisenberg chain. And the applied field itself was actually small. Okay? So in this limit, 2 pi r tilde is close to square root of 2 pi. By the formula I gave you an hour ago. Okay? So now let's go to our formula for the gap. So, according to this simple scaling analysis, okay, first of all, this is smaller than square root of 8 pi, so it's a relevant perturbation, so it must open a gap. And the gap scales like what? So lambda of 0 is h prime, so the gap is proportional to h prime to the 1 divided by 2 minus, okay, so here we had 2 pi divided by 4 pi, and so this is h prime, 1 divided 2 minus a half, which is h prime to the 2/3. Okay, so this very, very simple analysis basically tells you that in this case, if I take isotropic Heisenberg chain, if I put on a staggered field, I will open up a gap which scales like the staggered field to the 2/3. Yeah? And you have an exact exponent. And in the particular case I'm talking about, that's exactly what was observed. They observed basically a gap opened up. Yeah? The gap scaled exactly like the 2/3. Yeah? And it was described by this Side-Gordon model. Yeah? And then, okay, so you can exploit this. The Side-Gordon model has very, very rich physics, which is different from this Lambda-Liebig physics of the XXZ chain. And that was studied in great detail for this variety of materials. But the important point I'm trying to make is this very, very simple scaling analysis is very powerful. So you shouldn't scoff at this, yeah? So you should use it. So for example, I recently was sent a paper to referee, which I turned down, which contains some numerical analysis of a model like so, where they work very hard to calculate one of these exponents. But then this analysis actually gives the exponent in one line. Yeah? So then why would you want to torture the computer? Okay, so now I think I've run out of time. The last thing I had prepared, but which I can't do now, is, as I had pointed out to you before in this Bosonization formulas, when I express the spin operators in terms of the bosonic fields, there are also these higher harmonics, so 4kF, 6kF, 8kF terms. So if you want to know where they come from, you have to try to find me this afternoon. I can tell you in person. So that's all I had. Thank you for sticking with the lectures.
Thank you, Fabio. Are there questions? It's the last occasion, almost.
What about non-integrability of the last model? It just disappeared. I mean, so we started from a non-integrable Hamiltonian and then we just covered the same model.
Which is integral, yeah, so that is quite a nice coincidence, isn't it? I mean, so this is something that happens in a number of cases. So you have a lattice model, which is not integral, but in low energies, it's actually integral. So this is not an isolated case. I mean, so there many such cases exist. Yeah? Another case would be the transverse field easing model if you also put on a field in the longitudinal direction. It's also not integrable, but there's a scaling limit in which it's integral. So this is a very common occurrence, and if this happens, of course, you want to exploit it. Yeah? Because then you can use these methods of integrable field theory to say something about non-integrable lattice models.
No other questions?
Everybody's hungry.
Sorry. Thank you.